Welcome to this video on how to do elemental analysis. You can see here this is an elemental analysis machine. Let me get up my pen. So there's this machine where we put our samples in of compounds, usually accurately weighed compounds with a typical mass of 0.002 grams or less. And this is when we weigh these, typically in a lab we'd use a 4 decimal place balance. To weigh these samples we use up to a 6th decimal place balance. And these balances are so sensitive that the mass would change if you just breathed out on it. So these have to be kept shielded from wind, drafts and everything, these really highly precise balances. And then we just have a PC that records the data. And what you're concerned about is what the data is and how to manipulate the data to get an empirical formula. So we can analyze elements such as hydrogen, carbon, nitrogen, chlorine and bromine, and we can infer oxygen as well based on this. So element analysis determines the weight percent or the percentage of carbon, hydrogen, nitrogen, chlorine and bromine in a sample of an organic compound. This type of analysis doesn't usually detect oxygen, but we can infer the amount of oxygen by loss of mass. So this type of analysis is used to determine the empirical formula. So what happens in organic element analysis, what we do is we take our sample, it gets fully combusted. And when it's fully combusted, any carbon goes to CO2, any hydrogen goes to H2O, any chlorine will go to Cl2O, any bromine will also go to Br2O or other oxides. It's irrelevant as long as you know which oxide it is, it's okay. So this is how we can get, and obviously nitrogen will go to NO2. And what we can do is determine through the detector the amount of CO2, nitrogen dioxides, water, chlorine oxides, bromine oxides. And then once we know the ratio of these oxides, we can infer back the percentage mass of chlorine, bromine, hydrogen, nitrogen and carbon. The mass that's not detected will invariably be oxygen if it's a pure sample. So what data do we get? What we end up with is a percentage composition. So in this one we get a percentage composition table. Now what you can think of as percentage is just the grams per 100 grams. i.e. there's 17.85 grams per 100 grams or 17.85%. So these numbers here can be treated as being in grams, i.e. their mass. So these are essentially mass. And what we do to do this is, so we've got our little table. In chemistry, if we want to convert mass to moles, so mass to moles, we divide by the atomic weight. Okay, so for instance carbon would be 17.85 divided by 12 equals 1.486. Hydrogen, and you should try and use the precise masses, hydrogen would be 3 divided by 1.01. Nitrogen, there isn't any. Bromine would be divided by 79.9004. And that gets us these numbers. Now these are the mole ratio. Okay, and we want the mole, we don't want the mole ratio, we want them ratioed to 1. And the way you do that is you divide each by the smallest. So this is the smallest value. So we divide each by the smallest, so 0.99 gives us 1.5 Divide by 0.99 gives us 3. Divide by 0.99 gives us 1. Then once we've got this, we notice we've got a ratio of 1 to 3 to 1.5. Now in a chemical formula you never have halves, so we have to do something to get this to be whole numbers, and with any one of these tables, what you do to one column, what you do to one item in a column, you have to do to all. So in our first column we divided each number by its appropriate atomic weight. In the second column we divided each by the smallest. In this column we want to get rid of 1.5, and the way we do that is times by 2. And if we times that one by 2, so divide times that one by 2, so we have to times this by 2 and times this by 2, gives us a final ratio of 362. So we can then write the empirical formula, which is C. Ooh, can't write on that bit. Oh, that's the middle. So the empirical formula will be C3, because it's C3, H6, Br2. And that is our empirical formula. And the empirical formula is the raw ratio of carbon to hydrogen to bromine. It doesn't mean that in the molecular formula there is 3 carbons to 6 hydrogens to 2 bromines. That's just the ratio. It could be that the molecular formula has to be some multiple of this. So it could be the actual molecular formula is C6, H12, Br4, which matches this empirical formula. This is not the lowest ratio. The lowest ratio is 3 to 6 to 2, whereas this is 6 to 12 to 4. But this is the molecular, this could be the molecular formula, and this is the empirical formula, which is the lowest ratio. Okay, so let's just do another problem and see how you set it out. So what you would do is you get a table. So in this case we can dispense with nitrogen, bromine and chlorine because there is none. So you draw yourself a table. So the element, so in this case there's just carbon and hydrogen. You then need the mass, which, remember, this is just mass out of 100, so you can just treat it as raw mass. So we've got 85.63 and 14.37. Okay, you then want the moles, and the way we do that is we take 85.63, so 85.63 divided by 12.01 will give us, let me just get my calculator, so 85.63 divided by 12.01 gives us 7.12. Now it's important here to not round. Keep it out to 4 decimal places, and in fact that's a 9 there. Okay, then we do the same again. So what we do to one in the column, we do to the other. So 14.37 divided by its appropriate one, which is 1.01. So 14.37 divided by 1.01 gives us 14.227. Try and keep it to 4 decimal places, and I'll show you why in a few examples time. Okay, so that's our mole ratio. We then need to ratio to 1 to 1, and we do that by dividing each by the smallest. So if we do 7.1299 divided by itself is 1. Then we've got 14.22 divided by 7.1299 equals 1.995, which is close enough to be 2. So our ratio is 1 carbon to 2 hydrogens. Nice and straightforward. Now, if at here we end up with, say, 1.66, that is not close to 2, because x.66 is something and, so x and 2 over 3. Okay, so it's important. This is why we can't round here, we can't round there, unless it's close, i.e. within a decimal place of the whole number. This is not. Okay, so it's 0.266, so the 2/3. Or we could have 1.33. That is not 1. It is not close enough to 1 to be counted as 1. It is actually 1 and 1/3. Both of these, so when it's 1 and something and 2/3 and something and 1/3, the way we get rid of fractions is we do times by the denominator. So if we had that, we would times by 3. That would then, so 1.66 times by 3 should give you it should give you 5. Okay, so 1.66 times 3 would be 5. Okay, and that would be ratio to 5. Same with 1.33 times 3 will give you 4. Okay, this is important. Similarly, if your answer comes out at 1.25, that is a quarter. So you would times by 4 to get a whole number. If your answer came out at 1.2, 0.2 or 1.2, whatever, so 1.2 say, that one is a fifth, so you need to times by 5. So let me just take off the zeros and call it x 0.2, because that's what it really is. It's some number 0.25. Okay, another common one would be x.4, which again is 2/5, so again that's another times by 5. And that's probably the major ones that are going to turn up. Okay, and obviously the most obvious one is 0.5 times by 2. Okay, so let's do another example. So if I scroll down on here, okay, we've got now one that's a little bit more complicated, so let's create a new page. Do this again. So again, you can pause the video at this point before I do it and have a go yourself and then see if you get the same answer. So the important bit again is to put out elements, so carbon, hydrogen, nitrogen, bromine and chlorine. Okay, you want the masses, so 25.49, 5.88, 7.43, 42.39, 18.81. Next one would be, let me just put that line in there. Next one would be moles. So 25.49 divided by the molecular weight of carbon, which is 12.01. So 25.49 divided by 12.01. That would give you 2.1223. Then we got 5.88 divided by 1.01 for hydrogen. Will give you 5.8218. Nitrogen is 14.01, so 7.43 divided by 14.01 will give you 0.5303. Bromine is 42.39 divided by 79.904 for bromine would give you 0.53 18.05, which is essentially the same number as the nitrogen. Then we've got 18.81 for chlorine divided by 35.453 is again 0.5306. So we're going to divide by the smallest to get the ratio to 1. Okay, so the smallest is this number, although you could use the bromine result or the chlorine result because they're actually the same within experimental error. So let's ratio to 1. So 2.1223 divided by the smallest, which is 0.5303, gives us 4.0021, which is close enough to be 4, so we can just call it 4. We've got 5.8218 divided by 0.5303 gives us, well, it comes out as 10.98, but that's close enough to be 11. See, it's close enough to 11. The next we've got is, well, 0.503 divided by itself is 1. 0.5305 divided by 0.5303 will be 1, and that will be 1 as well. So we have our final formula of 41111. There's no fractions, so we don't need to times. So here we go. We can have C 4H11 NBrCl. Are we correct? Let's go on the slide here. Actually, on the slide here you can't see it. Okay, because this is not the PowerPoint, that's a PDF. But that should be the correct answer. Okay, I'm going to pause this, change to a new video now. So this is the instructional video. The next video will be going through a couple of examples from the work.